At the end of our last video, I asked you to draw as many possible isomers having molecular formula C5H10 that you could come up with. So let's start by analyzing the formula. You may recall that I told you that for a hydrocarbon which fits the general formula CnH2n plus 2, that hydrocarbon will not have any double bonds or triple bonds or any rings. Let's see if C5H10 fits. Well, if I plug in 5 to this equation, I'd have C5H12. So C5H12 would be the formula for a 5-carbon hydrocarbon that had no rings or no double bonds. So immediately you should realize that you're going to need to incorporate either a double bond or a ring. So let's go ahead and get started. And we can start where we left off in the last video, because we put together several different arrangements of the carbon atoms. Let's start by looking at those arrangements. The way we arranged the carbon atoms. First we had 5 in a row. Then we had 4 carbons in a chain with a 1-carbon branch. And then we had 3 carbons in a chain with 2 1-carbon branches. Let's just start by looking at our first arrangement for our carbons. Now, you realize that I'm going to have to put a double bond in these molecules, so let's just start at the end and work our way forward. So there we have our first isomer, and let's just analyze this quickly. See how many carbons we have, how many hydrogens. We have 1, 2, 3, 4, 5 carbons, and let's figure out how many hydrogens we would have on each of these carbons. So this carbon is already showing 2 bonds, which tells me that I need to add 2 hydrogens. So I'm just going to draw the numbers next to the carbons. This carbon showing 3 bonds, that tells me that carbon needs 1 hydrogen. Carbon number 3 already showing 2 bonds, which indicates to me that that carbon is going to need 2 more. So we need 2 hydrogens here. Here we need 2. Here we need 3. 2 and 3. So altogether I have 3, 4, 5, 6, 7, 8, 9, 10. So my formula is correct. Now I can put a double bond anywhere in that carbon chain and still end up with the formula C5H10. Let's just go ahead and move our double bond around. Now I can put my double bond here, and I'll leave it up to you to count up the number of hydrogens. You'll find that it's the same as the structure above it. What if I put my double bond there? Well, it turns out that if I put my double bond here, right, this molecule is the same as that one. And again, all I have to do is take this molecule and rotate it. All right, rotate it clockwise. I could rotate it counterclockwise, and that's going to return the molecule directly above it. So that molecule is not going to work. So let's see if we can move our double bond again. I can put my double bond here. Well, that's not going to work for me either, because this is the same as that. Again, all I have to do is rotate this molecule around. I can flip it over along an axis to make it look more like the molecule directly above it, or 2 molecules above it. So that doesn't give me anything new. So I've really exhausted all of the possibilities for that particular arrangement of carbons. Let's look at our next arrangement. Let's start adding in double bonds, because we already know that this particular structure has too many hydrogens. If I take away 2 hydrogens by adding in a double bond, now that'll reduce the number by 2. Here's our first structure. Let me just go ahead and count carbons for you again. I have 1, 2, 3, 4, 5 carbons. And then we'll just write in the number of hydrogens for each of those carbon atoms. Here I'll have 2. Here I'll have 0. That carbon already has 4 bonds. Here I have 3, 3, and 2. So I have 10 hydrogens on this molecule. Let's see again if we can move our double bond around. We'll start with the same arrangement of carbons, and we'll just move the double bond over here. That looks new to me. Right? That doesn't look like the molecule directly above it, and it's not. That turns out to be brand new. Let's try again. We can move our double bond over here. And that turns out to be new as well. We haven't seen that before. Let's try one final arrangement, or one final place for our double bond. What if I move my double bond right there? Well, it turns out that this structure, I haven't left myself very much room here, but this structure right there is the same as the first one. Right? So that one is not going to work. So again, here I've exhausted all of the possibilities for this particular arrangement of carbons with 4 carbons in a row and a 1 carbon branch. I can't put my double bond anywhere else and generate a new structure. Let's go ahead and move on. Now, how about this one? I already told you in the last video that the formula for this is C5H10, so I would need to add a double bond. What if I were to put a double bond right here? Well, if I did that, I have just violated the cardinal rule of chemistry, and I made a pentavalent carbon, or in other words, a carbon atom with 5 bonds, and that in chemistry is a huge no-no. It turns out that I cannot draw any structures having the formula C5H10 with this particular arrangement of carbon atoms. So I'm going to go ahead and erase this. But from the last video, you may have already realized that we can make some other arrangements. We can arrange the carbons in some other ways that give us the formula C5H10. I can put my carbons all in a ring. So let's make a 5-membered ring. And let's count carbons. I've got a pentagon here. You should be able to figure out pretty quick. I've got 5 carbons. 1, 2, 3, 4, 5. And let's figure out how many hydrogens each of those carbons needs. It turns out that each of these carbons is identical. They're all the same. And if I look at one of these carbons, I can see that it's showing 2 bonds, and that means that I need to add 2 more. So what I need to have over here are 2, 2, 2, 2, 2. That's the number of hydrogens that I need to add to each carbon to satisfy the octet for carbon. So 2 times 5 adds up to 10. So that works. There are a couple of other ways that I can arrange these carbons that will give me this molecular formula that I'm looking for. I can draw a 4-membered ring with a 1 carbon branch. Let's go ahead again and count carbons. 1, 2, 3, 4, 5. And let's figure out the number of hydrogens on each of these carbons. And this time I am going to draw them in for you. This one right here has only 1 bond showing. That means that I need to add 3. Let's add 1, 2, 3. Right now I'm just going to draw in the bonds. This carbon right here has 3 bonds showing, which tells you that I need to add 1. And the rest of my carbons are the same. They're all showing 2 bonds. That means that I need to add 2 hydrogens to each to satisfy their valence. And there we are. All of our hydrogens magically appear. There's a few more ways that I can arrange this. I've got a 5-membered ring, a 4-membered ring with a 1 carbon branch. How about a 3-membered ring, a 3-membered ring with a 2 carbon branch? Let's count carbons, just to prove to ourselves that we have the right number of carbons. 1, 2, 3, 4, and 5. And let's figure out the number of hydrogens that we would have on this molecule. I'll go ahead and draw them for you. So there we are. Our hydrogens add up to 10. I can draw a 3-carbon ring with 2 1-carbon branches. This will fit. I'm not going to add up all the carbons and hydrogens for you. I'll let you do that on your own. I can draw a 3-carbon ring, and I can have 2 1-carbon branches, but those branches can be in different places. And there we have it. Those are all of our isomers of C5H10. In summary, here's a much neater picture of all of the constitutional isomers of the formula C5H10.